Right, so this is lecture number 32. We are getting towards the end of the semester, and this will be the third lecture on the module on GPU parallelism. So in the previous lecture we had talked about CUDA C. So we had given you a hello world program in CUDA C that basically added two matrices or two vectors into a third vector C. So we saw that it's a three-step process. The first step is to allocate some memory on your device, and in this step you also copy the data from your host memory to the device memory. So that is for vectors A and B that have to be added. Then the step number 2 is to do the computations. So that is where you actually do write the kernel function which executes on each and every core of your GPU by running each and every thread on a single core. And then once the computation is done and you have added A and B into C on the device memory, the last step, step number 3 or part 3, is to copy that vector C from the device memory, that is your memory of the GPU, to the memory of your host, which is your standard RAM. And once you have done that, you also have to make sure you free or you deallocate the memory on your device. And once you have the vector C available on your host, you can do anything with it you want. You can either put it on a file, you can either put it print it on a screen, or do whatever you want with it. Okay. And remember, in CUDA you have two kinds of codes. So one is a code that executes on the CPU, that's called the host code, and then you have a code that executes on your GPU, that's called the device code. So this is a very quick summary of what we have discussed. Today what we will do is we will start with doing the same thing in Python, because remember it's always more comfortable to do things in Python than to do it in a compiled language. So it's always good to start with Python. In fact, in Python, if you deal with NumPy and other compiled modules, it can sometimes be as fast as a compiled language like C or Fortran. But again, it's something you have to analyze by yourself. So let's have a look at this code. So this code is already being pushed onto the repository. So let's go there, or let me explain the code to you quickly here. So you have some import statement. So you import NumPy, and you import Numba, which is basically going to give you the functionality of CUDA in this Python code. Then you import time as well, because you want to do some time calculations. So we set the size of the problem using setting this value n, which is typically expected to be large if you want to do lots of computations. Then you launch the CUDA kernel using this command called @CUDA.JIT. JIT stands for just in time compiler. Okay, so it's like a compiled code. So although it's a Python interpreted language, it's written in Python, which is interpreted language, but using this JIT, or particularly CUDA JIT, which is available through this module called Numba, it helps you create a compiled code, kind of compiled code, okay, which is compiled just in time. You don't need to worry about the understanding this, but basically this is required if you want to tell the program that this is going to you should be launching CUDA CUDA grids as a part of this code. The other flow is very similar to what we have done. So for example, you have this function called vector add, which again basically you have to write this @CUDA JIT before this function. Remember in this CUDA C, what we had done is we had given this keyword called __global __. So that told us that this is the host, this function is being called from the host, but it will run on the device. Okay, and I told you that there are other keywords available as well, which allow the function to be called from a device and launch on a device, or called from a host and run on a host, and so on. So this is something similar to that, which has to be specified before your kernel function. So vector _add is the kernel function here, which again is very similar. It takes in arguments a, b and c, which are basically the vectors a and b and c, and it takes the size of the vectors as well. Then you have a variable called idx, which is basically the same as what you had in CUDA C function. kernel function. So here we calculate the value of id x as the block id x dot x into the size of the block plus the thread id. Remember in CUDA, in GPU, the way it works is you have blocks of threads and each block has a certain size, and the thread numbering in each block starts from 0 all the way to the block size block dim dot x minus 1. Okay. So this is basically a formula to calculate the unique ID so that each and every thread can execute with this ID. And if this ID is less than n, because sometimes the situation can be there that the total size n does not fit exactly equal to the number of threads available, because the number of threads is number of blocks times the number of threads per blocks. So it may happen that this multiplication or the total number of threads available is slightly larger than the size of the problem. So you have to make sure that you only use the threads for which the ID is less than n. I mean, it should be equal to n, but the point, I mean, less than equal to, but in this case things start from 0, so you keep it less than n. Okay, and C of id is equal to A of id plus B of id. Okay, so this is the kernel function, exactly the same as what you had in CUDA. Then your main function. So in main function, remember it's a 3-part process. So again the code goes like this and then starts from the second column. So in the main function you have this h underscore a, h underscore b and h underscore c, which are the host memories. You have to allocate that. Then you have the device memories. So in this case the way you allocate the device memory, earlier you had this CUDA function for generating device memory. So here like the CUDA malloc. So here you have CUDA dot to device, which basically just declares and defines in the same step. So it copies h underscore a, which is the variable the vector available on host, into the device underscore a. Okay, so once you have done with the part 1, the next is to call this or run this kernel function. So the way you launch this kernel is by simply calling vector underscore add with the configuration parameters, which is your blocks, number of blocks and number of threads per block. Again very similar to what we had earlier. And then once you have executed that, you have to copy the information back to the host. So you say that d underscore c dot copy to host d h underscore c. So things in Python are slightly more intuitive, which is expected, and then once you have copied things, you can print them on the screen. Okay. So let's run this. So I already have downloaded the libraries required into a Conda environment, but you can do that easily. I mean, if you try to execute something, it will say this module is not available. So basically you have to install Numba and NumPy in this case. I'm just checking the environments available. So I think the environment I had set was CUDA. So I'll simply activate this environment. Okay. So I can also list what all libraries I had installed. So you can see that Numba is the font large enough for the people at the back to clearly see the screen. Can somebody at the back confirm? Should I increase the font size? Is it okay? Okay, good. So this is what this is a list of things I had installed. Again, if something doesn't work, it will suggest you what to install and you can install it. It's not that difficult to figure out these days. So once you have the right environment with everything installed in place, all we need to do is you simply need to, let's check. So we have the Python version available, and you have to make sure that the right Python version. I think Python versions beyond 3.10 do not support this library. So I mean, again, you can check it out. So let's launch the code, but for that we have to go in the right directory. So this is the Python code, vector_add. In fact, we can quickly have a look through it just to make sure that this is the code that we want to run. Right. So this is the Python code, which is the same as what I had shown on the screen, and this has a function main, and if you launch this code as it is, it basically checks if you're launching it by writing the Python running this code, and then it simply runs the main function. Of course, you could have named it something else, that doesn't matter. And we also have a time.sleep, which basically gives some time for us to figure out whether the code is actually running on the GPU or not by having a look at the memory utilization. So first let's run it without worrying about memory utilization, and then we will have a look at that. So we simply launch it by saying Python followed by vector_add.py. And now we can see that again it's very similar to what we had shown. So it shows the first 5 elements of the vector A. So it shows us the first 5 elements of A, B and C. So A and B are added. So A of 0 is 0, B of 0 is 10240000, that is the value of n, that is equal to n. And in the second element of A, B and C, so A of 1 is 1, B of 1 is n minus 1, and C of 1 is simply n again. So C is always going to be n because you are adding k with n minus k, so that gives you n in total. So this code is giving the right result, and now what we will do is we will execute, we will also see the utilization in task manager. So this is our GPU. So you can see that it's already using some GPU memory because I'm using this GPU for connecting the projector as well. But you can see that there was a small spike here in the memory copy of this GPU. So we can run it again, and then we'll hope that there will be a spike again because it copies the data into your GPU and then uses that. So you can see that there was a spike again here, and you can also see that there's a slight increase in the GPU memory during the part the code was running. So it's able to take the resources or use the resources properly. Is that clear? So I mean, this is another way for you to use your GPU cards if you are not interested in using or writing an ANSYS C. And personally, I would also go for this Python because it's always good to prototype things on Python first, and then you can use some profiling to figure out how long is it taking for it to run on Python versus how long does it take to run on with a CUDA C compiled code. But as I said, that this is a very simple code, and this is using just-in-time compiler, so it could happen that this is as fast as your C code. And again, if it's not a very long time that you're expecting the code to run for, it sometimes is much easier to write it on Python to save your programming time rather than writing it in ANSYS in CUDA C. But if you plan to run multiple instances or multiple times for different parameter values which expects to run on the cluster on the next few months, it's worth spending some time on optimizations. Right, so let's get back to our discussion. So what we'll do now is we'll talk about some ideas about dealing with multidimensional data, as well as some ideas about the architecture, the compute architecture of GPUs. So as I said earlier that I mean, you can also work with multidimensional data, like matrices are two-dimensional. So when you work with matrices on a GPU, the GPU should be able to handle that. In fact, GPU the way it the way it displays things, or the way we interact with the GPU, we can handle multi-dimensional blocks. So blocks need not be single dimensional, as well as each block has each grid has multiple blocks, so each grid can also be multi-dimensional. So that sort of matches with the dimension of the data. Of course, under the hood it may be working or linearizing or flattening the data completely, but for interacting from a user's perspective, we see the grids or the blocks to be multi-dimensional in nature. So we will have some discussion on that. So what we did was we had some configuration parameters when we called the kernel function. So remember, we said vec add kernel, and then we passed in the size of the grid, or the number of blocks in the grid, and then the number of threads available in the block. But that was only if you have a single dimensional grid and a single dimensional block. But if your grid and blocks are multi-dimensional, then what you need to do is you need to pass in these objects called in this case called, of course you can name them any way you want. So this is dim grid and dim block. So this is how you define the objects. So you say dim grid, it's of the type dim3, and then you pass on the dimensions x, y and z. So if it's a single dimensional grid, then you simply say 32, 1, 1 if it has 32 blocks in total. And then if each block has 128 threads, then you can simply say dim block, which is again a type dim3, is 128, 1, 1. But again the way it's it allows you by default to simply pass on the values 32 and 128 here if it's single dimensional. But if it's multi-dimensional, then you would actually have to pass, if it was 32, 2, then you will have to pass on dim grid rather than passing 32, 2 in this case. Okay. So, it is always safe to use this dim3 object and pass it on here in general. So, there are variables called grid dimension and block dimension, which are built-in variables. So, once you define your dim grid and dim block for a kernel, then inside the kernel function, if you want to use the values of this for example 32 and 128, you can extract that by using these grid dim and block dim built-in variables. So, if it was single dimensional, then you will simply say grid dim dot x, and that will return 32, because you have 32 blocks in a grid. If you said block dim dot x, that will give you 128, because you have 128 threads in a block. So, that is the dimension of a block. But if you had multi-dimensional grids or blocks, then you could access these y and z dimensional parameters as well using grid dim dot y, grid dim dot z, and similarly you could extract the number of threads in a block in the y and z directions as well. Okay. Some things to note. So, if you you will have multiple blocks in a grid. So, all the blocks will have the same dimension and sizes, which sort of makes sense, right? If you are launching multiple blocks, and blocks are individual units that are being launched on a GPU, each block should have the same dimension. It will get very confusing if one of the blocks is 2 dimensional, the other block is 3 dimensional, and so on. Similarly, each block should have the same size. So, that is the case. It's a restriction that all the blocks in a given grid have to be of the same dimension as well as size. And as of today, on the NVIDIA cards, you have a restriction that the total size of a block, the maximum size of the block can not exceed 1024 threads. Of course, it can have lesser number of threads. I think I have not worded it properly. The number of threads in a block cannot go beyond 1024. So, basically if you have block dim, which is the x, y and z dimensions of a block, If it's 512 comma 1 comma 1, that is allowed, because the total number of threads, which is this times this times this, is less than 1024. Similarly, these two are allowed, but if you take 32 comma 32 comma 2, that is not allowed, because that goes beyond 1024 threads in a block. Okay, so just remember that, or take a mental note that there is a restriction on the number of threads available in a block. So you have to choose your block dimensions appropriately in that sense. Now, one interesting thing which is something that we don't utilize a lot is that the grids and the blocks can be of different dimensions. So a grid is a collection of blocks, and each block is a collection of threads. So the grid, for example, in this figure that you have on the right, what you see is, if you look at kernel 1, which launches a grid, the grid is two dimensional. You have blocks in x direction and y direction. So you identify the blocks as 0 comma 0, 0 comma 1, 1 comma 0 and 1 comma 1. So typically the last dimension is x in the way we represent that, and the first dimension is z, which is different from the way we typically address the elements of any vector. But we don't need to worry about that, but it's a two dimensional block, grid, sorry. But each block could be three dimensional. I mean, the way the threads are organized inside a block in this example is, you have threads in the x, y and z directions. Now, if you look at the dim3 objects, so in this case dim grid is 2 comma 2 comma 1. So what that basically means is, it's a two dimensional grid, but if you look at the dim block, this is 4 comma 2 comma 2, so that's a three dimensional block. Okay, so this is again something one must know, which is a subtle feature of CUDA. Now typically we work a lot with 2D matrices. I mean, if you work with linear algebra and scientific computing, we end up working with matrices. So how do you store or use matrices with the GPU? So you use a two dimensional grid with two dimensional blocks. So if you look at this figure, what you see is that this is one big matrix which is broken into these blocks. So you have 1, 2, 3, 4, 5 times 4. So you have 5 blocks in the x direction and 4 blocks in the y direction, and each block has 16, is a size 16 by 16. So each block has 16 threads in the x direction and 16 threads in the y direction. So how will we refer to, let's say, the row coordinate in the matrix? So remember, each block has a numbering for threads which starts from 0. So let's say we are somewhere here. So we are somewhere here, and I want to figure out the row number. So what I need to do is, I need to start counting the threads in the block, but that will start from 0. So I need to add in the total number of threads in the previous block as well. So that's basically this formula. So you say that block id dot y, so this block id has a block id of 1 because id start from 0, times block dim dot y. So block dim dot y is basically the dimension of the block in the y direction, which is 16 in this case. So 16 times 1, that basically takes care of adding these 16 rows, and then you add the thread id x dot y, which is basically the number of rows in the block that you are sitting in. So that becomes the row number. Similarly, for identifying the column number in the matrix using this block id and thread id, you have this formula where you replace things with x, and this gives you the coordinates of the matrices of the matrix that you want to address, because remember, you want to send one element of the matrix to one core of the GPU. So you have to identify the mapping between the different elements of the matrices and block ID and thread ID variables. And as earlier when we saw this linear vector add function, your total number of threads available can be larger than the number of elements in the vector. Similarly, here also it can happen that your actual matrix size is such that the number of columns and the number of rows are lesser than the number of columns and number of threads available in the actual block grid system. So, you have to use an if condition, that if your row is less than the height and column is less than the width, you execute this. So, for the threads which are outside your requirement, you do not do anything with that, because there is no element of a matrix which maps with those threads. Now, this is something which gets a bit frustrating, but we have to deal with it, is that everything is flattened explicitly in terms of addressing matrices. Ideally, we want the matrices to be two dimensional arrays, right. So, that although the computer stores things linearly in the memory, because the memory is linear, as we discussed earlier in our many discussions, but we do not want to worry about that. Fortran uses a column major format where you store information in terms of columns. C uses row major format where you store information by rows. But again, why should we worry about that? But what happens is, since in examples like this we deal with situations where the arrays or the data structures are dynamic in nature. We do not know the size of these data structures beforehand, like we have done earlier, that the user specifies the value of n or something like that. So, when or even if you have specified the value of n in the code, you do not allocate the memory until you need it, right. So, if your memory is allocated when required, it is not a static data structure, then you cannot have a 2D or a 3D array in C or C++. That is the standard ANSI C or CUDA C requirement, that if you have a multidimensional array which is going to be allocated dynamically, then you cannot use it, basically you cannot have a multidimensional array that is allocated dynamically in C or C++. So, what do you do? Well, in that case, if you have a matrix like this, you have to store it like this, and that is basically how C would have done anyways, even if it was a static data structure, in the sense that you already knew during compile time what is the size. But that is okay. I mean, we just need to have this formula where if you want to refer to any element, you have to say row times width plus column. Okay. So, the computer will be I mean, for you as a programmer, you have to identify the unique ID in this linear flattened vector corresponding the mapping between the linear flattened vector and the matrix that you have. I mean, again, it is not a big thing, just some logic that you have to implement, but one must know that. So, this is a code. You do not need to have a look at the full code. I will just you just have to look at rows numbers, I mean lines number 6 and 7. So, you say the column number is block id dot x into block dim dot x plus thread id dot x. This is exactly what I showed you earlier. So, you have col and row which relate to the column and the rows of a matrix. Now, if things were allowed in 2D data structure, you would say that some matrix, let us say P out. So, P out of row comma column, and that will help you identify the element in the matrix. But since it is not allowed because these are dynamic, so everything is flattened explicitly. So, you have to convert that to an index in the flattened vector, but that is easy. So, the index of the flattened vector is simply row times width. Width is basically the number of elements in a row plus the column number. Okay. So, if you are basically you want to access, let us say M2 comma 1 here, that will be 1 2 3 4 5 6, okay, because M2 comma 1 well actually it's from top down. So this is m2 comma 1 is 4 plus 4 8 plus 2 10. So this is somewhere here. So m2 comma 1, so 2 comma 1 should map to 10 here. So the formula is 4 times 2, which is your width is 4, row number is 2 plus column which is 2 as well. So 8 plus 2 10. Okay. So this is just a mapping between a matrix which is 2-dimensional to 1D mapping. So once you have this gray offset, which is basically any index, you can pass this on. I mean, you can say P out, which is this vector of gray offset is equal to something. Again, this example is from another, it's not a matrix example, it is for an image manipulation, but even image is a 2-dimensional matrix as such. Okay. Now, if you are doing matrix multiplication particularly, so let us take this example. So, you are doing if P is equal to m times n. So, basically an element of P is a row of m multiplied by a column of n, right, that is what matrix multiplication is. So, this is the kernel function for that. So, you can see that we have row and column, which is exactly the same as what we had seen in the earlier slide, and then you have this condition where you say when if row is less than width and column is less than width. This is a square matrix. So, this basically means that if your total number of threads are more than the number of elements in the matrix, you have to make sure you only use the active threads. Then P value stores the element of the matrix P. So, P value is equal to P value plus, and you keep adding each and every m element of m multiplied by element of n, and you keep adding them. And once you have done that, you store that into P of row into width plus column. This is exactly what we mean by flattening the 2-dimensional matrix. So, that is the index for the flattened vector, and this is equal to P value. Okay. Right. So, this was on multi-dimensional arrays. Now, let us talk about compute architectures of GPU or compute architecture of GPUs, sorry. So, by the way, today we will talk about compute architecture, and in the next lecture we will talk about memory architecture, because that is also very important. It is important to understand how things, what are the compute elements available on the architecture of a GPU, but then we will also talk about the memory architecture and then relate the two or understand whether our code is underutilizing the compute architecture or the memory architecture, and how to effectively write a code which best utilizes the both. So, there is something called a streaming multiprocessor. Okay. So, this is typically written as SM, and if you look at the architecture of a GPU in the figure on the right hand side, you see these blocks. Well, I should not use block, but these sections called SMs, different SMs are there. So, typically a GPU, and all these green things are cores. So, if you add all the green boxes, you get the total number of cores available in a GPU. Okay. So, physically each GPU has something called streaming multiprocessors, which are these blocks. So, each streaming multiprocessor has some number of CUDA cores or cores, which are these green boxes. Okay. And these streaming multiprocessors will, so all the cores in streaming multiprocessor will share some memory and control logic. So, you can see that there is some memory which is shared between the streaming multiprocessor cores. Similarly, there is a control logic portion which allows the instructions to be given to the cores, which is also shared between the cores available in the in a given streaming multiprocessor. So, just to give you a perspective, let us talk about my machine, the laptop I am using. So, this is RTX 4050, which is a laptop GPU card. It has 20 streaming multiprocessors and 128 cores or the green boxes on each streaming multiprocessor. That gives us a total of 2560 cores in total. Similarly, if you look at V100, which is the card available on Param Himalaya, that is 80 times 64, that is the architecture of the card. If you talk about A100, which is better than V100, then you have 108 times 64. So 108 streaming multiprocessors and 64 cores on a streaming multiprocessor. So again, architecture varies depending on the card that you have, but you need to have some understanding of that, as we will see later. And when we talk about memory, although we will talk more about it in the next lecture, but you can see that there is something called an on chip memory, which is on the chip of the compute chip. So this is basically the memory available on the streaming multiprocessors, that is called an on chip memory, and there is an off chip memory, which is basically the memory that you see here. So when I say the device memory, typically that refers to this global memory, which is the memory of the GPU card. So if you buy a GPU card which says 16 GB, so that 16 GB is your off chip memory or the global memory. So off chip does not mean that it is not on the GPU card. It is on the GPU card, but it is not in the streaming multiprocessors, it is outside that. Okay. Okay, so a couple of things about, so now you may get confused that what is a streaming multiprocessor and what is a block, because we said that when you launch a grid, the grid has blocks and blocks have threads. Now we are talking about streaming multiprocessors which have cores. So see, streaming multiprocessors are hardware units and cores are again hardware units, and blocks and threads are logical independent threads or collection of threads launched by a program. So we have to map these blocks of threads onto the hardware that we have, which is streaming multiprocessors. So what happens is all the threads in a block, so basically a whole block goes to the same streaming multiprocessor. It cannot happen that half of the threads in a block go to one SM, the other half go to the other SM. So the whole block goes into one streaming multiprocessor, whichever it is. And typically the blocks are small in the sense that multiple blocks can fit on a streaming multiprocessor. Okay. Now there may be exceptions sometimes, but this is what a general situation is in most cases. So don't bother yourself too much with it. But this is an ideal situation, typically that the whole block goes into a streaming multiprocessor, and typically you will have multiple blocks that can fit in a streaming multiprocessor. In fact, when you launch threads using a kernel in a CUDA C code or a CUDA Python code, you generate many more blocks that than the number of blocks that can execute on a given streaming multiprocessor. So if your streaming multiprocessor can fit 3 blocks, you generate 6 blocks for that SM. So what will happen is, first 3 blocks will execute, then after that in a sequential fashion 3 more blocks will execute on the same SM. So this is the job of a runtime system. I mean, if you have a GPU card which is large enough, which can fit all the blocks, well and good, all 6 will run on the SM. But if the GPU card is like a laptop card, a few may run and then the other blocks will run after that. Now what happens is, since all the threads in a given block go to the same streaming multiprocessor, the interaction between the threads of a block and the interaction between threads between blocks is different. So for example, if you want to have a barrier synchronization, it's much easier to synchronize the threads on a given block because all these blocks are going to the same all these threads in a block are going to the same streaming multiprocessor. Okay. So basically the idea is that the whole block goes to a given SM. So let us talk about barrier synchronization and then we will stop. So synchronization is something we have discussed earlier, barriers in OpenMP for example, or MPI. So you put a barrier, so that means all the threads have to report to that barrier and only then you can proceed from there, and this is something we need in many times because you want to make sure that all the work has been done. So for this is a code where you with an example of a barrier. So you this is an incorrect code, but that tells us, so this underscore sync threads is basically a barrier. So this is saying if thread ID is even, then you do this, if it is odd you do this. But remember earlier we said that if you have a barrier, all the threads, in this case all the threads in a block have to report to the barrier, only then the code proceeds from there. So if you have this barrier here, then what that means is all the threads in a given block have to report to this barrier, but by logic only the even threads will report to this barrier. So this code is going to hang. Okay, so this is incorrect code. So typically in GPUs all the threads in a given block have to report to the barrier call that you have. If you have a call for a single thread in a barrier, all the threads have to report to that barrier. And the reason we have these threads in a block reporting to a barrier and so on is because they are closely spaced with each other in terms of time and space. So they have the same shared memory available, they have they are all equally privileged in a sense. So all the threads in a given block typically behave as if they have to synchronize with each other if there is a barrier call available. Okay. So let us stop here, and I know that we are discussing a lot of abstract ideas, but we will try to implement or use as many as possible. But again remember, this is a first level course. I want to make sure that you get some idea of how GPUs work and what are the typical constraints available on a GPU. And if you want to do more advanced things for yourself later in research or other applications, you should be comfortable expanding your understanding. Thank you.